Faraday's law of induction, or just, I guess, Faraday's law is what we say, is that there is an induced EMF, which I'm writing as E sub L, which is equal to the negative of the derivative of the magnetic flux with respect to time. And that magnetic flux, not through it over an entire surface enclosing a volume, but over a partial surface. That magnetic flux is the integral of B dot dA. It's familiar because it reminds me of the electric flux in Gauss's law. So some things that I'm familiar with. So when I look at Faraday's law, one of the key features that it has is that there will only be an induced EMF when this integral, the integral of B dot dA, has time dependence. If the integral of B dot dA turns out to be a constant in time, then take the derivative is zero, there's no induced EMF. So the law implies exactly what we observed, that if the flux does not change, then there's no induced EMF. So I want to look at this flux integral here and ask the rather obvious question, under what circumstances would I find a flux integral that is time dependent? Well, I'll see that immediately by breaking out the dot product B dot dA. As we all know, this scalar product B dot dA is the magnitude of B times the magnitude of dA times the cosine of the angle between them. And so my answer becomes immediately apparent. I will encounter an induced EMF if the magnetic field is time dependent. Well, that's a rather obvious one. If the magnetic field changes in space, naturally the flux would change. But I also would get an induced EMF if the area changes. When I did my demonstration, I didn't have the opportunity because my solenoid is very rigid. But if I had a loop of wire near a magnet and I crushed that loop of wire, changing its area, I would, if it were connected to a meter, see a deflection because there would be an induced EMF because the area would be time dependent. If the area were time dependent, then the flux is time dependent, and then the derivative would be non-zero, and I would get induced EMF. Also, the angle. If the angle is time dependent, that is, if I change the orientation of the loop in space, that will change the flux in time, and that will induce an EMF. And then, of course, I could have any combination of those time dependencies, and if I really, really disliked students, I could invent a problem where the magnetic field was time dependent and the area was time dependent and the orientation of the loop in space was time dependent all at once in one problem. Although it turns out that almost never happened. I'm not going to say never because, of course, then it'll immediately happen. Yeah, and as a matter of fact, to you that might sound like a curious thing. When would that ever happen? But it turns out to be a stunning technological application. But you'll see, because I'm going to do, my organization for today's discussion is to do each one of these dependencies. Right? So I'll start with magnetic field as a function of time, and then area as a function of time, and then angle as a function of time, and you'll see how that plays. Because L is a symbol that's chosen for electromagnetic induction. There are lots of cases that have come along where we choose a symbol for a thing that doesn't immediately make sense to us, like B for magnetic field. And you need to know a better reason than M is already mass. And so using M for magnetic field is probably a bad idea. Well, in our next set of lectures after this one, I'm going to describe inductor, which is an electrical component, and the symbol for their inductance is L. And so L is typically used for description of this type of inductive. There may be a deeper reason for that, but I've never actually researched it as to why L was chosen. It's entirely possible that it's just a linguistic artifact, like it comes from the French or the German or the Latin or something like that. So magnetic field is a function of time, area is a function of time, angle is a function of time. And I'm going to do those three things as my essential calculations related to Faraday's law of electromagnetic induction. And I should be able to get it all done on the one board here. So I'm just going to call this magnetic field as a function of time. Here I've written B as a function of time dependence. So I'm just going to fabricate a problem. This is not a very general situation. It's very specific. This is perhaps like a problem that I could be asked. So in a sense, this description that I'm giving you is a little bit practical because I'm on the verge of discussing the trials and tribulations of solving problems relative to this type of physics. Imagine that I have a magnetic field that is uniform in space everywhere. That is, the magnitude and the direction of the magnetic field is constant everywhere, and it is directed straight up from the floor to the ceiling. And I'm going to change my mind about that. It's not directed straight up, but it is uniform in magnitude, direction everywhere in space. I'll draw it on my diagram. I'm going to place a circular loop in this magnetic field. Now, I've drawn the circular loop as sort of an oval here, and so you have to have an idea about the three-dimensional nature of it. So, as I've done before, I'm just going to mark this as the near side. So the bottom side there is near to you, so you get an idea of the three-dimensional perspective of it. So I have a magnetic field that is uniform everywhere in space. And here is the magnetic field, B. And it's at an angle, I'm going to say an angle theta, with respect to the plane of the loop. Now I've said that this magnetic field is uniform everywhere in space, which means there's no area dependence. That is, there's no time dependence on the area. The magnetic field never changes with respect to the area, and the area of the loop doesn't change. And the loop is fixed in place, so there's no angular dependence. I'm going to put the time dependence explicitly in the magnetic field, and I'm just going to make something up. This is not fundamental. I'm just going to make up a time dependence. I'm going to say that the magnetic field is negative 5 t squared plus 3. I just made that up. Just fabricated that right off the top of my head. Obviously, this magnetic field fluxes the loop. And because the magnetic field changes as a function of time, there will be an induced EMF. I'm going to use Faraday's law of electromagnetic induction. I'm going to use Faraday's law to find the magnitude of the EMF. And then I will use the right-hand rule, well, you will use the right-hand rule, in order to determine the direction of that induced EMF. So, in order to get this done, I'll write that the induced EMF, according to Faraday's law, is equal to the negative of the derivative with respect to time of the integral of the magnetic field dotted into the differential of area. And here comes the very first part where I have deliberately brought in some problem-solving strategy into this. The dot product is B dot dA, and I have deliberately on my diagram drawn the wrong angle. This is a place where students often get burned because they go along and apply equations, just jamming along equations trying to solve a problem and don't think about it. The dot product tells me that it's the integral of B dot dA, which is the integral of B times dA times the cosine of the angle between the magnetic field vector and the differential of area vector. The differential of area vector is perpendicular to the surface of this loop, not parallel to it. The angle that's given is the wrong angle. The component of the magnetic field that I want is the component of the magnetic field that actually fluxes the loop. It's this component of the magnetic field, if you'll forgive the strange notation, the perpendicular component of the magnetic field. That's the component that I want. That's the component that I want. And so I have to play heads up with that. That is a gag that happens in our physics very often. We're like, wah, we gave you the wrong angle and you fell for it. Trying to determine if students are actually thinking about the quantities involved as opposed to just plugging and chugging. So what I'm going to write here inside the integral is B dA times the sine of theta. Times the sine of theta. Because that gets me the component of the magnetic field that is perpendicular to the loop. Right now, as I perform the integral, I'm not concerned about any time dependence at all. I'll perform the integral first. I do not need to plug in that the magnetic field is a function of time because the magnetic field is a constant with respect to the area. It comes out of the integral. And so to show that, I'll put an algebraic step here where I write that the induced EMF is the negative of the derivative with respect to time of, I'm going to put parentheses. I don't think I've ever done that before, but there you go. The magnetic field times the sine of theta. Both are constants with respect to area times the integral of the differential of area. Well, that got simple real quick. What do I get when I integrate over the area of the circular loop? The entire area of the loop. I didn't give the area of my loop a radius, but let's go ahead and say that it has a radius r, then its area is pi r squared. That's perfectly fine, I can do that. And so what I have here is that my induced EMF will be the negative of the derivative with respect to time of the magnetic field B times the area, which is pi r squared, times the sine of theta. But the only thing in there that has time dependence is the magnetic field. So what I'm going to do is take the negative of the derivative with respect to time of, well, actually, here's what I'm going to do. The magnitude of the induced EMF, and so you know in the very next step here I'm going to drop the negative sign. The magnitude of the induced EMF is going to be equal to pi r squared sine theta times the derivative with respect to time of B. But B is negative 5t squared plus 3. Well, that derivative is quite simple to take. The magnitude of the induced EMF then, dropping the negative sign that's going to appear in my derivative, is just 10 pi r squared sine theta times t, because the derivative of negative 5t squared plus 3 is 10t. And I'm taking the magnitude, just drop the negative sign. Notice that the magnitude of the induced EMF is not constant in time. It's perfectly fine. You can have a time-dependent EMF. You can have a time-dependent EMF, no trouble there whatsoever. So I found the magnitude of the induced EMF is a function of time. And what I find is that it changes linearly. The sine of theta is a constant, 10's a constant, pi is a constant, r is a constant, and so it changes linearly in time. Here's my question. Right-hand rule time. And a little bit of very careful thinking, because this is really the hardest part of it. The hardest part's not the algebra. Some careful thinking. Viewed from above, what is the direction of the induced EMF in the loop? Is it viewed from above clockwise or counterclockwise? Don't blurt it out. Take a moment to think about it. I have to take a moment to think about it. Clockwise or counterclockwise? Do I get a vote? What do you got? Counterclockwise, Jules says. And some bobbleheads back there are nodding for you, Jules. They're in your favor. Does anybody say clockwise? Anybody care to say clockwise? Oh, yeah. This problem, it can change, and it's going to change in the next one, but not in this one. So I guess everyone agrees with Jules that the answer is counterclockwise. I'll point my thumb in the direction of the magnetic field that is upward. But because of the time dependence, that magnetic field is actually decreasing. And so the flux upward is decreasing. The loop will help it counterclockwise, viewed from above. Congratulations to those of you who agreed with that, because it's actually quite rare. Usually we get a 50-50 split on whether it should be. Everybody's agreed. Counterclockwise is the direction of induced EMF. And so the strategy here is I use Faraday's law, careful application, I get the magnitude of the induced EMF, and then I use the right-hand rule in order to determine the direction meant. Now, area as a function of time. The problem that I'm about to demonstrate here is a super classic. It has appeared on our exams so many times, and you'll find in your homework assignment it appears quite often. It is a classic problem. And it's drawn a little bit 3D, so you might struggle with it. It took me some time to get it exactly right. I have two bars, metal bars like this, and they are perhaps equal in length. It's not a requirement, but they are parallel to each other, but I'm going to draw them in 3 dimensions. So in order to make it look sort of 3-dimensional, I'm skewing one bar over this way, thusly. I'm going to take these two ends here and connect them with a resistor. And then I'm going to lay across the bars another metal bar that is not fixed to them, so that I can slide it back and forth. By sliding the metal bar back and forth, I have a rectangular area that I can make larger or smaller as I choose. I can make larger or smaller as I choose. At any given instant, you can't abbreviate that. Any given instant. The width of this apparatus is W. No, sorry. The width of this apparatus I'm going to call L, and this, I'll call this the length of the area, and we'll call this the width of the area at any given instant in time, length and width. And so calculating that rectangular area is quite a simple thing. So the length times the width. But if I take the bar and I move it along, then the area will increase as a function of time. And so this is how I'm going to create an example problem to solve, where the area is a function of time. But this one is much more fundamental than my first example. I'm going to move the bar along this way with a velocity v. Move the bar along with a velocity v in this direction, and that makes the area get larger as a function of time. I need some magnetic field. So to make things simple for myself, I'll choose a magnetic field that is uniform in magnitude and direction everywhere in space, directed upward. And so inside this region here, I have a magnetic field that is directed upward and fluxes. I've made it easy on myself there by not putting in an angle. I need not find any components. The magnetic flux through the loop would simply be that magnetic field multiplied by the area of the loop. And that would be the magnitude of the flux that I have at any instant. So I'd like to calculate the induced EMF in this instance. And so the EMF induced is going to be equal to, you know what, I'm going to go right for the magnitude this time, and to hell with the negative sign. The magnitude of the induced EMF is going to be the derivative with respect to time of the integral of the magnetic field dotted into the differential of area. But the magnetic field is perpendicular to the area. And when I'm performing the integral, I don't care about the time dependence of the area. The time dependence of the area is not relevant to the integral. It's relevant to the derivative, but not the integral. So the integral of b dot dA simply becomes b times dA. So the derivative with respect to time it becomes b times dA. The magnetic field is constant over the area. It comes out of the integral, and so this simply becomes b times A, as I alluded to before. And I think that's something that you're all very familiar with. Pardon me for just a second. I'm doing area-dependent flux. What are you doing?
I'm doing scoring. What am I always doing?
The magnetic field is not a function of area. It is uniform over the area, so it comes out of the integral. Then the integral of dA is A. So now what I find myself doing is computing the derivative with respect to time of the magnetic field times the area. But of course, the magnetic field, the magnetic field is not a function. The magnetic field is not a function of time. So this is the magnetic field times the derivative with respect to time of the area. Well, what is the time dependence of the area, the explicit time dependence? Turns out I have to invent that. So let's consider that the bar is moving at constant speed. If the bar is moving at constant speed, well, under any circumstances, the area of the rectangular region is equal to the length of the region multiplied by the width of the region. Well, the width of the region is getting larger and larger and larger according to the constant speed. So this is where my time dependence comes in, because it becomes the length times the initial width plus the velocity times time. A little kinematics. It's a little x is equal to x naught plus v times t. Yay, I love that. Back to the good old days. So now I have the area with explicit time dependence, and I'll plug that in down here. This is the magnetic field multiplied by the derivative with respect to time of the initial area plus the velocity multiplied by time. Well, look, that's a very easy derivative to take. The initial width, oh, pardon me. Do you want me to multiply that L through? I don't want to. The derivative with respect to time of the initial width is 0. The derivative with respect to time of Vt is V. And so what I find here, a very classic result that you're going to see over and over again, and would not be surprised if you saw it on one of our exams. That is the magnetic field times the length times the velocity. That is a very, very classic problem of electricity and magnetism, one that is frequently asked. There are some ancillary ideas that I could get into here. I'm going to discuss more in the following lecture, but my question for you right now is, viewed from above, what is the direction of the induced EMF according to the right-hand rule? Note, the magnetic field is completely constant. Steve says clockwise. Brad agrees. Magnetic, right? So as the area increases, we agree, clockwise. As the area increases, the flux upward is increasing. The loop will oppose it. My fingers curl in a counterclockwise direction, or I'm sorry, in a clockwise direction from above. I'm going to build a special kind of apparatus. I'm going to have a loop of wire that has these two leads off the end of it, but I've got to be able to turn this loop of wire in space. And so I need to have these little special attachments that we put on it that are not actually attached to it, but can just touch it to make electrical conduction. And then down it comes to my meter so I can measure. So they just sort of make contact. They're just metal in contact there. So I can spin the thing around about its long axis. I'm going to be able to rotate this circular loop. Let's say it's a loop of radius r, and so its area is pi r squared, and is a constant. And it rotates with a constant angular velocity omega. Oh, jeez. You know how that, I just got the width naught plus vt there, little kinematics. It was the width plus v. It's going to be as complicated as that. All right, so relax. I need some magnetic field. I have a magnetic field B that is uniform in space, but what happens is the differential of area of the loop is perpendicular to the loop, and when the loop rotates at a constant angular speed, that differential of area vector goes around like a lighthouse. And so its area with respect to the magnetic field changes as a function of time. The angle changes as a function of time. So let's calculate the magnitude of the induced EMF. Of course, well, it's the derivative. I'm dropping the negative sign because I'm looking for the magnitude. The derivative with respect to time of the integral of the magnetic field dotted into the differential of area. Well, that, of course, is equal to the derivative with respect to time of the integral of the magnetic field times the differential of area times the cosine of the angle between them, where the angle is time dependent. Well, good for the angle. The time dependence is not relevant to this integral. The integral is over the area. So the time dependence of the angle is not relevant to the integral. All of it comes out of the integral, and I'm doing the integral of dA. So what this turns out to be is the derivative with respect to time of the magnetic field times the area times the cosine of the angle between them. And the magnetic field and the area have no time dependence. The magnetic field and the area have no time dependence, so they come out of the integral. This is the magnetic field times the area, derivative with respect to time of the cosine of the angle. The angle does have time dependence. So just like I did in this rectangular area thing, I have to insert that time dependence. I have to insert that time dependence. Well, how am I going to do that? Well, it has an angular speed omega. Therefore, the angle is equal to the initial angular speed, the initial angular position plus the angular velocity times t. There's no angular acceleration. See, I'm doing a theta is theta naught plus omega naught t plus 1/2 alpha t squared, but there's no angular acceleration. There's no angular acceleration, so it's just theta is equal to theta naught plus omega t. You know that I can choose that initial angle to be 0. Come on now. Now I can put the time dependence in because this becomes BA, the derivative with respect to time, cosine omega t. The derivative of cosine omega t is omega, it was negative omega sine omega t. Negative omega sine omega t. So what I get for the magnitude of the EMF, and I'm going to drop that negative sign, what I get for the magnitude of the EMF is BA, well, I guess I'm going to put in the area if you don't mind. Area is pi r squared omega sine omega t. That is the magnitude of the induced EMF. That is the magnitude of the induced EMF. Notice, it's still time dependent. Not only is it still time dependent, but it's time dependent according to a sine function. And that sine function is going to go +1 and -1. That sine function is going to go +1 and -1. If you were to make a graph of the EMF as a function of time, it would be a sine function. And so the induced current, notice I'm not asking you the induced current would alternate. It's alternating current. This is how the human race generates electrical power. Yeah, where are you going to get your DC from? From batteries. Good luck. So I build myself a fire. I have a tank of water. I boil the water. It creates steam. I use the steam pressure to turn a turbine. The turbine is connected to a loop of wire that rotates in a magnetic field. Or I let the water go over the dam. The water goes through the turbine, turns a turbine, which is connected to a loop of wire that turns in a magnetic field. But sadly, nuclear. I have a nuclear reaction that boils water. The steam pressure turns a turbine that turns a loop of wire in a magnetic field. Sadly, but wind power. I have the wind blowing across turbine fans that rotates a loop of wire in a magnetic field. The only thing that's not this for power generation is batteries, the chemical reaction, and solar panels creating electrical power through the photoelectric effect. Yes, rotating a loop of wire in a magnetic field, generating electric. There was a wonderful back in the day, there was a Sports Center gag where they're in Sports Center and they're like doing their reporting in their cubicles and the lights go out. So like Rich Eisen goes down the stairs into the basement and he opens like a janitor's closet and Lance Armstrong's sitting there on a bike like toweling himself off. And he's like, yo, Lance, what's up? He's like, oh, sorry. And he starts pedaling again, powering the whole building. So here it is. Ah, you bastards. Kids play with this and then. Go, Charlie, go.
Pedal. We need a little hint.
Magnets. Inside there, loop of wire, crank handle, turning a loop of wire in a magnetic field, generating current. That's why I alluded to, Sarah, that's a big deal. Rotating a loop of wire in a magnetic field by electromagnetic induction, generating current. This is a fun thing to leave laying around because the next thing you know, ladies, and I say ladies specifically, boys are going to start shocking themselves with it. One time a young man spent 5 or 10 minutes electrically shocking his sandwich and then ate it on a dare. And I'm there like Willy Wonka. I'm like, you know that doesn't. You just. And they'll put their fingers on it and crank it. They'll put their tongue on it and crank it. And anybody who walks in what's that? Yeah, little electrodes here. You can get quite a shock off this thing. There's a fun little feature too that if I turn it, but Charlie, it's so difficult to crank. Of course it is. I'm doing work to turn the crank that is the energy that is being turned into luminous energy in the light bulb. Well, yes, it's a very small radius, so I have to exert large torque. But if I take out the light bulb, it's easier to crank. Law of conservation of energy. I'm not creating light, so I don't have to put as much energy. And you can actually feel it in the crank, that it's easier to crank because there's no light being created. Yeah?
Like say if evaporating.
We do use different, yes, but not on large scales. So I can answer your question, yes. People do build little electrical generators using like isopropyl or something like that because it boils at a very low temperature. Okay. But on large-scale power generation, we always use water. Also, freon gas is sometimes used. Yeah. I'm sorry? These are magnets. These are horseshoe magnets here. And so they're bent like this, so I get a uniform magnetic field between the tines here and here. And then in there's not just one loop of wire, but many loops of wire that are being turned simultaneously. And when you have many loops of wire, you just put a factor of n in your equation. So if you have 2 loops, you get twice the EMF. And if you have 1,000 loops, you get 1,000 times the EMF for every crank that you do. And so, power generation. So I'll leave this laying out tomorrow morning and then the nonsense will begin. And they won't be able to help themselves, even though I said it. Even though I said it out loud, boys would be like, ah!
They don't want to. Now they're going to want to shark their sandwich.
Jules, like, you're not going to be in it? I'll put it right here.
I'm not going to do it. It's against my principles to touch other stuff like that.
Oh, you have my permission, Jules.